Welcome to the Deep Dive. You know, the show where we dig into the sources and pull out the key stuff so you can really get informed. And just think about it for a second. The air around you right now.
Yep, that's a solution. A gaseous one.
Your coffee this morning.
Definitely a solution. Aqueous, most likely.
Even the oceans, right? It's all these, like, uniform mixtures. They're everywhere.
Absolutely fundamental. And so many chemical reactions, the really important ones, happen in solutions.
So today we're doing a deep dive into Zumdahl, and DeCoste's chemistry, specifically Chapter 11.
Right, all about the properties of solutions. It's a fascinating area.
Exactly. And our goal here is pretty simple. Get you through the main ideas, the theories, what it all means in the real world. Make it stick, even without any pictures or diagrams.
Think of it as a fast track to really understanding the chemistry behind, well, almost everything we encounter.
Okay, so let's dive in. What is a solution, fundamentally?
Well, the key term is homogeneous mixture,
Homogeneous meaning.
meaning it's perfectly uniform. The components are mixed right down to the molecular level, so you can't see different parts. It looks the same throughout.
And it's not just liquids, right? You mentioned air.
Exactly. Solutions can be gases like air, liquids like, say, vodka or salt water, or even solids.
Right.
Think of alloys like brass that's a solid solution of copper and zinc.
Huh. Okay. But this chapter mostly focuses on liquids.
Primarily, yes, and especially aqueous solutions, which just means water is the solvent, the thing doing the dissolving.
All right, so their mixtures, their composition can vary. How do we talk precisely about, how much stuff is dissolved beyond just strong or weak?
Yes, we need quantitative measures. First, you've got the solute, that's what gets dissolved, and the solvent, the dissolving medium. Usually the solvent is whatever you have the most of.
Solute and solvent. Got it.
Then we have four main ways to describe the concentration. First up is molarity, capital M.
Okay, molarity. I remember that one. Moles per liter.
Moles of solute per liter of solution. That distinction is important. It's super useful in the lab, but the catch is it changes slightly with temperature.
Because volume changes with temperature.
Exactly. Volume expands or contracts, so molarity isn't constant if the temperature fluctuates.
Okay, what else?
Then there's mass percent. This one's pretty straightforward.
Just the mass of the solute divided by the total mass.
Mass of solute divided by the total mass of the solution times 100%. Simple, intuitive.
Makes sense. Number 3.
Mole fraction. Usually written with the Greek letter chi.
Mole fraction.
It's just the ratio. Moles of one component, say, the solute divided by the total moles of everything in the solution, solute plus solvent.
So it tells you the fraction of molecules that are solute.
Kind of, yeah. It's about the relative number of moles. Unitless.
Okay. And the last one.
Molality, lowercase m. This is moles of solute per kilogram of solvent.
Per kilogram of solvent, not solution.
Precisely. And because it's based on mass, not volume, molality is temperature independent. That's a huge advantage sometimes.
Right? Masses don't change when you heat things up. So molarity, mass percent, mole fraction, molality.
Those are the big four. You might also occasionally run into normality, capital N, especially in acid-based stuff. It relates to equivalence, like how many protons an acid can donate.
Okay, like sulfuric acid, H2SO4, has 2 acidic protons.
Exactly. So a 1 molar solution of H2SO4 would be 2 normal, because each mole provides 2 moles of equivalence, in this case protons.
Gotcha. So this brings up that challenge question you mentioned earlier. Can one solution be more concentrated by mass percent but less concentrated by molality than another?
Yes, absolutely. It seems counterintuitive at first, but think about it. Mass percent considers the total mass. Molality only considers the solvent's mass.
So if the solvent in one solution is much heavier, like its molar mass is way higher.
Or if the solute itself is really heavy compared to the solvent. You could have a high mass fraction of solute, but if the solvent it's dissolved in makes up a relatively small mass portion compared to the solute, or if the solvent itself is very dense, the molality moles per kilogram of solvent could actually be lower than another solution where the mass percent is less impressive.
That really makes you think about what each unit is actually measuring. Okay, so we know how to define and measure solutions. But why do things dissolve? What's driving it? We hear like dissolves like all the time.
Right, like dissolves like is the classic rule of thumb. Polar things dissolve polar things. Nonpolar dissolves nonpolar. Water and ethanol mix, oil and water don't.
But what's the chemistry, the energy behind it?
Okay,
Right.
Picture the dissolving process in 3 energy steps. Step 1, you have to pull the solute particles apart, break their intermolecular forces. This takes energy.
Endothermic.
Step 2, you have to make room in the solvent, push its molecules apart to create cavities. This also takes energy.
Endothermic again.
Step 3, now the solute and solvent particles mix and interact. This usually releases energy as new, favorable attractions form.
Exothermic.
Often, yes.
That.
So the overall NLP change for the solution, epsilon, is the sum of these three, H1 plus H2 plus H3. It can be positive, negative, or close to zero.
So for oil and water.
For oil and water, H2 is huge because you have to break water's strong hydrogen bonds. And HH3, the interaction between nonpolar oil and polar water, is pretty weak. So the total energy change is large and positive. It's just energetically unfavorable to mix.
It's for salt in water. NaCl.
There, H1 and H2 are also pretty large. You're breaking ionic bonds and hydrogen bonds. But HH3, the energy released when water molecules surround the Na plus and Cl ions, called the enthalpy of hydration, is also very large and negative. It almost cancels out the first two steps.
So the overall energy change is small. Why does it dissolve so well then?
Great question. This is where entropy comes in. The universe tends towards more disorder, more randomness. A dissolved state with ions scattered throughout water is much more probable, much more disordered than having separate salt crystals in pure water. Even if the energy change isn't hugely favorable, the large increase in entropy drives the process.
It's not just energy, it's probability too. Fascinating. How does this connect to, say, health?
Big time.
Yeah.
Think about the pesticide DDT. It's nonpolar.
So it dissolves in fat.
Exactly. It's fat-soluble, builds up in animal tissues, causes major problems. That's why it's banned in many places.
Okay. What about something beneficial?
Well, take vitamins. You have fat-soluble ones, A, D, E, K. They're mostly nonpolar, stored in body fat. You can actually get too much, a condition called hypervitaminosis.
Right.
Then you have water-soluble ones like B vitamins and vitamin C. They're polar, lots of OH bonds. They dissolve easily in water, in your blood, and if you take excess, you just excrete it.
Which is why sailors needed lime's constant vitamin C source.
Precisely. Prevented scurvy. It all comes down to molecular structure, polar versus nonpolar dictating solubility. Same reason barium sulfate is safe for X-rays. It's ionic, but the ions are locked so tightly together it's incredibly insoluble in water, even though B2 plus itself is toxic.
Yeah. Okay, so besides the nature of the solute and solvent, what else affects solubility? Pressure. Temperature.
Definitely. Pressure is huge, but mainly for gases dissolving in liquids.
Like soda.
Perfect example. Henry's law describes this. It says the concentration of a dissolved gas, C, is directly proportional to the partial pressure, P, of that gas above the liquid. C equals K times P, where K is a constant.
So high pressure in a can means lots of CO2 dissolves. Open it.
Pressure drops, P goes down, so C goes down, and the gas fizzes out. It goes flat as it reaches equilibrium with the lower CO2 pressure in the air.
And you mentioned Lake Nyos earlier.
A tragic natural example. Huge amounts of CO2 dissolved in the deep, high-pressure water. Something disturbed it. The CO2 rapidly came out of solution, flowed downhill, and suffocated thousands. A direct consequence of Henry's law.
Chilling. What about temperature?
Temperature effects are a bit more varied. For most solid solutes in water, solubility increases as temperature increases. Think dissolving sugar in hot tea versus iced tea.
Easier when it's hot.
Usually. But there are exceptions. Some salts, like cerium sulfate, actually become less soluble as temperature goes up. You really have to determine it experimentally.
Okay. And for gases?
For gases dissolving in water, the trend is much more consistent. Solubility almost always decreases as temperature increases.
So warm water holds less gas, like oxygen.
Exactly. This is the basis of thermal pollution. When industries dump warm water into lakes or rivers, the dissolved oxygen level drops, which can be devastating for fish and other aquatic life.
And boiler scale.
That's often related too. Water can contain dissolved calcium bicarbonate. When you heat it in a boiler, CO2 becomes less soluble and escapes. This shifts the equilibrium, causing insoluble calcium carbonate limestone, basically, to precipitate out and form scale, clogging pipes.
So these solubility principles are everywhere. How do we use them deliberately, maybe to separate things?
That leads us straight into chromatography. A brilliant technique. Let's take thin layer chromatography, TLC, as an example.
Okay, TLC. I've seen those plates.
Right. You have a plate coated with a stationary phase, usually something polar like silica gel. Then you have a mobile phase, a solvent, which moves up the plate.
And you spot your mixture at the bottom.
Exactly. As the solvent moves up, it carries the components of your mixture with it. But here's the key. Components that are less polar interact less with the polar stationary phase, and are more soluble in the often less polar mobile phase, so they travel farther up the plate.
While more polar stuff sticks to the plate more.
Precisely. It has a higher affinity for the stationary phase and moves slower, not as far. So, based on their differing polarities and solubilities, the components separate out at different heights. It's all about that, like, dissolves, like, principle and action.
Very clever. Okay, moving on. You mentioned earlier that solutes can change the properties of the solvent itself. This is where it gets really interesting, right? Colligative properties.
Yes, colligative properties. This is where things get cool because these properties depend only on the number of solute particles dissolved, not what they are. Doesn't matter if it's sugar or salt or something else, just how many particles you have.
Just the concentration of particles.
Exactly, in an ideal solution. This makes them super useful for things like determining the molar mass of an unknown substance.
Okay, what are they? You mentioned four.
Right. First is vapor pressure lowering. Adding a non-volatile solute, something that doesn't evaporate easily to a solvent, always lowers the solvent's vapor pressure.
Why does that happen?
Think of the surface. The solute particles take up some space, so fewer solvent molecules are at the surface able to escape into the gas phase. It literally reduces the escaping tendency.
Okay.
This is described by Raoult's law.
Huh.
The vapor pressure of the solution, Zom, equals the mole fraction of the solvent times the vapor pressure of the pure solvent.
Solvent. Fossils.
Right. And because vapor pressure depends on the number of particles, if you dissolve something like NaCl, which breaks into two ions, Na plus and Cl, it lowers the vapor pressure roughly twice as much as dissolving the same number of moles of sugar, which stays as one particle.
Uh-huh. So it tells you about dissociation too.
It can, yes. Those solutions aren't always perfectly ideal. Sometimes solute-solvent interactions are stronger or weaker than predicted, leading to deviations from Raoult's law.
Okay, vapor pressure lowering. What's next?
Boiling point elevation. This follows directly. If the vapor pressure is lower, you have to heat the solution to a higher temperature to get its vapor pressure equal to the surrounding atmospheric pressure, which is the definition of boiling.
So adding solute makes the boiling point go up,
Yep.
like antifreeze stopping boilover.
Exactly. The change in boiling point E is proportional to the molality of the solute particles. NEHT is just a constant specific to the solvent.
Okay. And the op?
Freezing point depression. Adding a solute lowers the freezing point. The solute particles disrupt the process of solvent molecules organizing into a solid crystal lattice.
Like salting roads in winter.
Perfect example. Salt dissolves, lowers the freezing point of water below 0 degrees C, so the ice melts. The formula is similar. To melt TT, include KFM, where KF is the freezing point depression constant for the solvent. Adding solute basically widens the temperature range where the solvent stays liquid.
Makes sense.
Yeah.
And the fourth one, osmotic pressure.
Right, osmotic pressure. This involves a semi-permeable membrane, one that lets solvent molecules pass through but blocks solute particles.
Okay.
If you have pure solvent on one side and a solution on the other, there's a net flow of solvent into the solution side. That's osmosis.
Why does it flow that way?
It's partly entropy, again, mixing is favorable. Also, the solute particles on the solution side effectively lower the concentration of water there, reducing the rate at which water molecules pass back out of the solution compared to the rate they pass in from the pure solvent side.
So there's a net flow in.
Yes. And osmotic pressure is the external pressure you'd need to apply to the solution side to stop this net flow. The formula is Adiel's MRT, where M is molarity, R is the gas constant, and T is temperature.
This sounds really important biologically.
Hugely important. Osmotic pressure is very sensitive, even for dilute solutions, making it great for finding molar masses of huge molecules like proteins. It's the principle behind dialysis artificial kidneys using membranes to clean blood. It governs how IV fluids interact with cells' isotonic, hypertonic solutions.
Right, cells shrinking or bursting.
Exactly. Crenation or hemolysis. It's why salting meat or sugaring fruit preserves them. It draws water out of bacteria cells, killing them. And if you apply pressure greater than the osmotic pressure...
You can push water the other way, out of the solution.
Yes. That's reverse osmosis, how we get fresh water from seawater in desalination plants. You force water through the membrane, leaving the salt ions behind.
Incredible applications. Now, you hinted earlier that electrolytes, like salt, behave a bit differently because they break apart.
Right. For electrolyte solutions, we need to account for the fact that 1 mole of solute might produce 2, 3, or more moles of particles. ions. We use the Van Hoff factor.
IF factor.
It's defined as the moles of particles actually in solution divided by the moles of solute formally dissolved. So for NaCl, ideally I2. For KCl2, ideally I33.
Ideally.
Yeah, in reality, especially in more concentrated solutions, the observed I value is often a bit lower than the ideal integer. For zero point 0.1 molar NaCl, I might be around 1.87, not 2.
Why is that?
It's due to ion pairing. Oppositely charged ions occasionally bump into each other and stick together briefly, acting like a single particle for a moment. This reduces the total effective number of independent particles.
So it slightly reduces the colligative effect.
Exactly. So the modified colligative property equations become AT, IKFM, AT, IKBM, and AMRT. You just multiply by the Van Hoff factor.
Which explains why sports drinks have electrolytes. Those ions affect osmotic balance.
Precisely. Maintaining hydration and cell function.
Okay, one last area. What about particles that are bigger than dissolved ions or molecules, but too small to just settle out? Colloids.
Ah, yes, colloids or colloidal dispersions. These are mixtures where tiny particles, roughly 1 to 1,000 nanometers in size, are suspended throughout a medium. Think milk, fog, jello, paint.
Bigger than molecules, smaller than grains of sand.
Kind of, yeah. They're in that intermediate range, and a key way to spot them is the Tyndall effect.
The light scattering thing.
Exactly. Because the particles are large enough to scatter light waves, a beam of light passing through a colloid becomes visible, like headlights in fog, or a laser pointer beam through slightly dusty air. True solutions, with much smaller solute particles, don't scatter light like that.
So what keeps them suspended? Why don't they just clump up and settle?
Usually it's electrostatic repulsion. The surfaces of the colloidal particles tend to absorb ions from the surrounding medium, typically all the same charge, so the particles end up with charged surfaces that repel each other, preventing them from aggregating.
Do you break a colloid to make it clump?
Sure, that's called coagulation. You can do it by heating, which gives the particles enough energy to overcome the repulsion when they collide, or you can add an electrolyte. The ions from the electrolyte neutralize the charges on the particle surfaces, allowing them to stick together when they collide.
Like river deltas forming.
Perfect example. Clay particles suspended in river water are colloids. When the river meets the salty ocean water, an electrolyte solution, the clay particles coagulate and settle out, forming the delta. Same principle used in electrostatic precipitators to remove soot particles from smokestacks.
Fascinating. It connects everywhere.
It really does. Nature's even figured out how to use proteins to control ice crystal growth in polar fish, which scientists are now studying for things like making better ice cream.
Amazing. So, wrapping this up, we've really covered a lot of ground on solutions.
We definitely have, from the basic definition, homogeneous mixtures, to the different ways we measure concentration, like molarity and the temperature-independent molality.
We look at why things dissolve, that balance of energy changes in breaking and forming interactions, plus the drive towards entropy, all summarized by like dissolves like.
Then the factors affecting solubility, Henry's law for pressure on gases, and the different effects of temperature on solids versus gases, leading to things like thermal pollution.
And those powerful colligative properties, vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure, all depending just on the number of solute particles.
Don't forget accounting for electrolytes with the Van Hoff factor and the unique world of colloids, scattering light via the Tyndall effect.
It's clear these principles have just immense real-world impact. Our bodies, our environment, industry, food.
It's chemistry that's constantly at work, often unseen.
So, for you listening, the next time you mix sugar in your coffee, see salt on the road, or even just breathe the air, maybe pause for a second.
Yeah, you're witnessing this incredible interplay of molecules, energy, and entropy, all governed by the principles we've talked about.
What other everyday things, what other bits of magic could be explained by this hidden chemistry? Something to think about. Thank you for joining us on this deep dive into the properties of solutions. Keep learning, keep asking questions.
And we'll catch you on the next deep dive.